All right, well, good afternoon and welcome everybody. Thanks for coming to the session. We've got a lot of interesting stuff to take a look at here regarding Windows and containers from the experts. Perhaps the company that produced the most transformational DevOps tool that we've seen in the last decade, Docker and Mirantis. I'd like to introduce Deep and Zhang.
Hi, everyone.
Thank you. Thanks. Hope everyone's having a great KubeCon so far. Welcome to the afternoon session around superpowers for Windows containers. So presenting the session would be Rouge, my coworker from Docker. He's a very active SIG Windows contributor. And I, Deep Debroy, I'm an engineering manager at Docker and tech lead over in SIG Windows. So the agenda for this session, roughly we are going to go over a very quick intro to the history of support for containerized workloads in Kubernetes for Windows, and then go over the concept of privileged operations and the support for that in Windows containers, which pretty much does not exist at the moment. We'll look at a possible workaround that the community has sort of agreed upon, which is based on this concept of privileged proxies. We'll look at the specific design of such a privileged proxy for the area of persistent storage. We'll look at how privileged proxies can potentially be used in other areas like networking, diagnostics, and so on and so forth for Windows nodes, and finally conclude with future directions and a demo. So very quick introduction to the history of Windows containers. Windows Server 2016 was the first LTS release when initial support for containers made it to Windows. A lot of enhancements were made between 2016 and 2019 through the RS3 and the RS4 releases. And along the same time, a lot of folks from SIG Windows has been concentrating on getting the kubelet and other components of Kubernetes up and ready for Windows node support. So finally, around Kubernetes 1.14, the overall Kubernetes community and SIG Windows was ready to declare stable GA support for Windows workloads. And as you guys probably heard in the session right before, Introduction to Windows, a lot of work is upcoming to build support for containerd and things around those lines in 1903 and in future versions of Kubernetes. So here's a very quick overview of how, and a very high-level overview of how Kubernetes clusters with Windows and Linux nodes look like. The control plane still runs completely on Linux masters, but for the worker nodes, you can have a mix of Linux and Windows. So the Windows nodes are going to run the pods that comprise of containers whose base images are Windows base images. They would be running your Windows workloads as well as the kubelet kubeproxy and plugins necessary for storage and networking. The Linux model does not change. The Linux workers run pretty much the same set of stuff. Now, one interesting deficiency or limitation for the container support in Windows is there's no concept of capabilities. This is something you might be used to in the Linux world, where every container can be assigned a specific set of capabilities all the way up to something called privileged, which allows a container to have full access to the host and perform a wide variety of operations on the host that otherwise a regular container cannot do. In case of Windows, that option is not there. So as a result, a lot of privileged operations cannot be easily performed by Windows containers. Some of these involve accessing and managing the host registry, managing host network configuration if you want a Windows container to be in charge of networking for the rest of the other containers in the host, which is typically a case for CNI plugins, and the ability to access and manage storage devices such as disks, volumes, and so on from the host. This allows a container encapsulating, say, CSI node plugin logic to be able to provision storage for other containers running on the host. So given this lack of ability, pretty much Windows containers are a bit handicapped when it comes to acting as full-fledged Kubernetes daemon-sets. This specifically becomes a problem when you're thinking about CNI and CSI plugins. So the community started thinking about that. We discussed it quite a bit in SIG Windows, and storage was one of the areas both Jean and I are interested in. So we're looking at it also from the storage perspective. And we came up with a bunch of different options or workarounds for this lack of privilege support. One is just allowing a container remote shell access into the host. Obviously, this sounds very dangerous, but it could be achieved over something like, say, Secure Shell or PowerShell. But it's very challenging to constrain the set of operations that a container can perform on the host. It's completely unfettered access. So this was too radical a thing, and the community decided against it. Another process or another approach that was thought about was how about the base desire was the ability to ship out logic within containers. So what if there was something called a specialized runtime class that the Windows runtime surfaces that allows a container image to come down into the Windows node, but the payload be extracted and launched as a process. Now, this could be achieved through extensible container runtime like, say, Containerd, which allows you to write specific shims. So you can run something called a process shim that needs to be designed that allows you to extract a payload from a Windows image and run it directly as a host process with all the privileges of say, a Windows service. However, this is not a container. And this, again, allows for fairly unfettered access into the host and was kind of considered a bit too radical to start off with. So what we eventually decided on is this mechanism called a privileged proxy, which is basically specific logic that's coded into a binary that needs to be run on the host. And a bunch of different containers can access the privileged process to accomplish the set of operations that they need. And this is going to be the focus of this presentation.
So that approach, basically, it's just going to be a raw binary that's running on the host itself. That's going to run with admin access, and so can do whatever it wants. And then exposes the capabilities that it has through namepipes, so that namepipes can then be mounted in containers, and containers can have privileged access to the host that way. So hopefully that means that this binary needs to somehow make it to the worker and somehow be run. So there's no good solution. There's no standard solution for that. But that's something that admin clusters today are used to dealing with on Windows because they still have to, today they still have to make sure the kubelet is running, the kubeproxy is running, that Docker-D is running. So we don't have a good solution for that, but it's not really a new problem either. So whatever your distro uses to get the kubelet on the node and running, you can use for a proxy as well. And the good thing, one of the good things about this design is that the supported operations by the proxy can be scoped to OS subsystems. And so it's really easy for the proxy to enforce constraints and restriction as to who has the right to do what, as opposed to what Deep was talking about before, having remote access to the host. This really allows a fine-grained control on what containers can actually do through the proxy. So the architecture looks something like this. So this whole image is a Windows worker. So you have your kubelet running, Docker-D, and the kubeproxy running. So these are what you need today to have your Windows worker node in your cluster. And so adding a proxy is just adding yet another binary that's running, and that's exposing its capabilities through namepipes. And these namepipes can then be mounted into your pods. So that's the manifest file you have to the right. Just using mount path volume mounts allows to mount the pipes in the container that you want to be able to use these capabilities, and then they can make remote calls into the proxy and do what they need to do this way. So this manifest file shows how easy it would be to use that to have privileged containers to do what you need to do, and use that for example, CSI or CNI plugins, the same you use to on Linux today. So considerations for deploying this proxy. That's one of the things we brushed on before. Yeah, that binary needs to be somehow run and managed. Not a new problem, up to you. But one of the good things about this proxy is it's really easy to have control on who does what. And one of the ways to do that would be using pod security policies and admission control webhooks to decide which pods and which namespaces actually have privileged access to the hosts. So let's look at what that would look like in practice. So using pod security policies, you could have that use that pod security policy, and we bind that cluster role to everyone. So by default, once you do that, no one can use volume mounts in your cluster anymore. And so that way, people can't use the name pipes that the proxy exposes. For the pods and the services that you do want to have using your proxy, then you create a new pod security policy, which has the host path capability in the volume mount. You create a cluster role to use that security policy, and then you bind that cluster role to whichever namespace and service accounts you want to allow to use the proxy. Another really big benefit of the proxy, the whole philosophy of the proxy idea is to really expose the most low-level possible capabilities of the OS through the proxy, so that the hope there is that the API should be fairly stable, and then plugin vendors, plugin authors can rely on somewhat reliable and somewhat stable APIs to have their own release cycles on top of that. So for example, you can have an API to create directories or see if one exists. That's unlikely to change much. So having that stability at the API level allows plugin vendors to really have their own release cycles without relying too much on improvements to the proxy. So we can have like really decoupled life cycles for containerized plugins and the proxy itself. And so once you have that, you can use the proxy to develop containerized plugins and do the same as people are used to on Linux today. So having CNI and CSI plugins come in as kube workloads, Daemon-sets, and whatnot. And Deep is going to go into how we adapted this proxy ID to do storage.
Thanks, Sean.
That's great.
So basically, the first use case that we looked at was storage. CSI was becoming really popular. And just to give you a quick introduction to how storage support, persistent storage support works for Windows today, is it's based on two models that are being deprecated pretty soon. One is the entry plugin model. The community does not want specific cloud provider logic or logic from specific storage vendors within the Kubernetes code base. So they want to get rid of entry plugins from inside Kubernetes into external plugins that are in a completely separate code base. So the entry plugins that Windows depended on are kind of on a path towards deprecation. The other model is using Flex Volume plugin scripts, but Flex Volume itself is also considered pretty much deprecated for Linux. It's kind of like one of the ways out for Windows, so it's not completely removed, but it's there, but it's also considered essentially deprecated. In both of these approaches, you notice that with the kubelet-based approach for entry plugins and the Flex Volume, there is direct access to the disk devices and the volume devices in the host because everything is running directly on the host. Nothing is within a container. So just to kind of put it in a diagram, kubelet and the Flex Volume scripts, they're running directly on the host. They have direct access to the device handles for the disks. They have full capabilities to mount a SMB share remotely and then surface them up to a Windows pod or the containers within a Windows pod. However, the future is based around the container storage interface, which is CSI. Now, CSI is a very detailed topic, so let's focus mainly on the aspect of CSI that concerns Windows. There's a concept of CSI node plugins, where the node plugins implement the logic to identify, say, a LUN that gets surfaced to a node. Based on the LUN, once it has identified that it's a LUN that belongs to the driver that it implements, it can partition it the way it wants, format the file system, and surface it up to containers. So the node plugins essentially implement the modern CSI spec with GA'd around 1.13. Typically for Linux today, the CSI node plugins are distributed as containerized binaries, and they are deployed through privileged pods in Linux. So for Windows, the desire is to have a very similar mechanism. And this fits very nicely with the privileged proxy concept. We want the CSI node plugins to do a whole bunch of privileged operations as we went over. And the idea with the CSI proxy is to have a privileged proxy that surfaces a bunch of APIs through named pipes up to the CSI node plugin containers so that they can do whatever it is that they desire to do. For example, scan the physical disk objects based on their SCSI page 83 or page 80 identifiers, initialize a disk, partition it, format a partition with the file system they want, mount SMB shares, interact with iSCSI targets, like logging into a target, logging out, exchanging credentials, and so forth. So as you see, the model changes from kubelet and a bunch of flex volume scripts having direct access to the devices in the host to actually a CSI node pod, which is essentially comprising of a couple of containers, the CSI node driver registrar, which is used for registering a plugin with CSI, and the CSI node plugin core logic that's shipped by a vendor, all wrapped up within a couple of Windows containers and shipped as part of a Daemon-set specification. The CSI node pod will mount the name pipes exposed by the CSI-Proxy.exe, and through the name pipe, it can make API calls down to the proxy to get access to the devices from the host. And finally, once it has formatted the volumes or identified the volumes that it needs to surface up, it can just create the necessary symlinks in the file system of the Windows pods to make the volumes available in the containers.
So one problem that surfaced when we submitted a CAP for the proxy for CSI, what people wanted to have a mechanism that would make it easy for the proxy to evolve, to add new capabilities and modify existing ones. That would be easy for developers working the proxy and yet ensure API stability for plugin authors that would use the API. So one way we came up with to solve that problem is just reusing the same thing Kube itself does on its API. So we recycled the notion of API group and API versions. So the capabilities the proxy exposes are grouped by API groups. So typically there's an API group for disk and volume operations. There's another one for iSCSI operations, and so on and so forth. And each API group can have, in a given version of CSI-Proxy, for each API group, you're going to have one or several versions of the API that are running. And then the API versions are maintained and deprecated according to a release schedule that's also pretty similar to what Kube does. Internally, though, for maintainers of the proxy, you don't want people to have to duplicate a bunch of code when they create a new API version. You want to be able to reuse most of it because it's just going to change something for your new version, add a new capability or change an existing behavior. So internally for developers, you want to have a single internal representation of what the version APIs use. So you can have request and response types for each API endpoint. And each version might have slightly different semantics for each of these. But internally, you're going to have only one presentation for each API group for all these types. And every single internal representation should be able to contain all the information contained in all the versions of the same type. So that, of course, means that you have to have a bunch of conversion code to take a version request, turn it into the internal representation, and then back to the version response. So we also did what Kube does internally, and we have a bunch of code generation in the CSI proxy. So as a developer, if you want to add new capabilities to the proxy, the source of truth for every single API version is going to be in a proto file. So in this, the blue files are the files that need to be maintained, and the green files are the ones that are auto-generated. So as a developer, if you want to add a new version, you need to create a proto file that defines what your API version looks like, and then you need to add the right types to the internal types.go. And of course, you need to write the server's logic for it. So how do you take a request and turn it into a response? And all the rest is auto-generated. So we generate conversion code to convert from version types to internal representations. And then we also auto-generate code to create the right name pipe to expose your new capability. And we also auto-generate client code that can be imported into projects that use the proxy as a library. So the idea here is to make it easy for developers to contribute to the project. Of course, auto-generated conversion only works if you have one-to-one mapping from the version types to the internal representation. So that's where you might have to do some manual code to say, okay, like this version type, that's how we turn it into the internal representation. But hopefully the goal here that you only have to do that when it's not trivial. To deploy proxy versions to cluster, that's what cluster admins need to know. So basically, when you administer a Windows cluster and you want to use the CSI-Proxy, you need to understand which API group and versions matter to the plugins you want to use. And you want to ensure that the version of the CSI-Proxy you're running actually caters to the plugins that you care about. So hopefully, plugins should stay roughly in sync with the latest version of CSI-Proxy. If they don't, and you need to run a very old API group and version, that's possible. It's possible to run several versions of the CSI-Proxy at the same time to be able to support everything you need. And that's it. Deep is going to do a little demo for us.
All right. So here we have a Windows node that's running our CSI-Proxy.exe. Let's get this started. And what you see here in the good old disk management UI is a freshly formatted VHD that we would like to create some partitions in from inside a container. This is something you cannot do from a regular Windows container. But what we did is we created a container called partition demo. We made it mount the proxy pipe as Jean just described. And we are passing it a parameter of disk ID of 4, which is the disk ID here. And before we get started, let's look at disk part. So we see detailed disk. There are no volumes in there. So let's run the container.
Oops.
Hold on. Maybe it's a different.
Start the proxy.
Give me 1 sec. There is probably another. Sorry about that. Let me try to increase the font real quick. All right. So it's kind of the same setup. What we saw here is essentially, sorry. Sorry about that. So yeah, we ran the container over here. We are running the CSI-Proxy, and what we did is we had disk number 2, which was there as an unpartitioned disk initially. And from inside the container, it mounted the v1 alpha 1 pipe with the disk API set and invoked the necessary commands to first check whether disk is initialized. If it was not, it initialized it with, say, the MBR partition format, or you could do a GPT, and then checked if the disk was partitioned. And since it was not, it created a raw partition on disk. So again, the gist of this is this could not have been possible from a regular container, but because it's mounting the named pipe exposed by CSI-Proxy, it talked over an API with CSI-Proxy to make these operations happen. Yeah, that's pretty much the demo. Let's switch back. So storage is not the only use case, but the first use case we decided to look at. The same model could be applied to networking. CNI plugins are an obvious candidate for the same model. If there are folks interested in working on a community-managed proxy for HNS API calls, that would be great to have to kind of get the community moving in that direction. Node monitoring and diagnostics tools could be another interesting use case where you have a community-maintained proxy that collects event logs, ETW log traces, et cetera, from the host and transmits it over an API to containers that you deploy as Daemon-sets. There are various avenues through which you can get involved. If you're interested in contributing to the CSI-Proxy project, here are some of the details. Overall, you can just stop by SIG Windows and talk about an idea, and we can help you get maybe a KEP started. That's what we did with CSI-Proxy, kind of got it reviewed with architecture, security, and storage, besides Windows itself. So we can do the same for other areas like networking, diagnostics, and so forth. There are the Slack channels, and especially around CSI Windows, we have a weekly sync up. Right now, we have Jean, myself, KK from Azure over there, and Jing Zhu from Google, who contributes to the project pretty actively. So thank you. That's all we had. Any questions?